My name is Eoin O'Mahony. I manage the data science group for matching high-capacity vehicles and shared rides at Uber. I've been at Uber about 4 years and been working these problems the entire time. So what is matching at Uber? Yes, I used to hit the right button. Matching is a core technology at Uber. It's very much part of what makes Uber Uber. And the matching teams at Uber are responsible for figuring out how to match riders and drivers across our networks. So if you push a button and request a ride, how do we think about what driver we should offer that request to? And if you take a shared rides product like Pool or Express Pool, how do we think about finding other riders that could share the ride with you to result in a lower price? We've invested heavily in this technology over the past couple of years. Now we have systems that handle millions of requests globally, and we've actually had a lot of innovation in this space. And innovation in this space allows us to have a much more efficient and much more elastic network. To give you an insight into this, I'm going to talk through a quick history lesson of matching at Uber. So the first versions of matching at Uber were very much a greedy algorithm. So a request would come in, we would look at the available drivers, and then we would send the request to the nearest driver. Now, Uber used to initially treat the nearest driver via something called Haversine distance. And this is a straight line distance where you take the curvature of the earth into account. I've dug into this for years and still can't figure out why we made that decision. As an example of this, if you go from San Francisco to Palo Alto, the difference between Haversine and Euclidean distance is about 10 meters. So I'm pretty confident that in the history of the company, this hasn't ever really mattered in making decisions. But there has been a lot of wasted arctan computations on our servers. So if you think about matching in a straight line, if you have a small ride sharing network, that works fine. But if you think about how you as a rider experience Uber, people experience Uber in terms of time. So if you look out into a dense urban geography, you have things like one-way streets, rivers, highways, bridges, and straight line distance doesn't capture that. So after that, Uber moved to assigning drivers based on nearest in terms of drive time. So computing for each driver, how long it was going to take someone to pick someone up, and then going for the driver that would get you in the car the fastest. And that worked really well for years. However, something challenging about matching at Uber is that it's an online problem, being that the decisions you take in the moment impact what decisions you can take in the future. Let's take a concrete example. We have rider A opens up the Uber app and requests a ride. And they're matched with driver A, that's 2 minutes away. So everyone's happy, that's a great match. However, a couple of seconds later, we have rider B come in. And they're matched with driver B, that's 9 minutes away. And neither rider nor driver are gonna be happy with that. That's not a great ETA. So what could we do differently? Well, what if instead of when rider A comes in, instead of matching them, we actually wait a couple of seconds. And then in that time, we see rider B requests come in. And now we can think about doing something that's better for the network as a whole. So we could actually realize we can match rider B with driver A at 4 minutes and rider A with driver B also at 4 minutes. So although rider A is a slightly longer ETA, we've actually saved the system as a whole 3 minutes. Now, when we start making these small network optimizations across something the size of Uber's network, this adds up to a huge amount of time. In fact, every day we save years of time through optimizations like this. And this is pretty compelling because we're giving riders back time, so they're less time traveling somewhere. And also for drivers, we're giving them less on route time, which means more time earning. So investing in matching, by waiting a couple of seconds, we get a lot of gains in the efficiency. However, we can take this even further with our products like Pool and Express Pool, where we're asking people to wait for a couple of minutes and Express Pool to also walk. This allows us even more flexibility where we can have far more potential routes evaluated, look at other pairs of riders and drivers and riders and riders, and end up in far more efficient routes and a far more efficient system. And we can actually take this efficiency and give it back to our riders in the form of lower price and also result in better, more efficient routes for our drivers. However, once you increase the wait time and increase this possible space of routes, the computation really becomes a problem. And actually we spend a lot of time thinking through how do we solve these hard computational problems in a real-time system? So I'm going to hand it off to Danny in a second, who's going to talk through high-capacity matching. And something that's really exciting here is we're able to take a lot of the learnings we had from building Pool and Express Pool and scale those up. So instead of putting 3 people in a Prius, how do we use that same technology to efficiently put 14 people in a minibus?
How's everyone doing? Bear with me, I'm an engineering manager at Uber. I manage the overall matching team. I'm Owen's engineering partner. Our team is focusing on the core business for Uber, mainly UberX and Uber Pool. And today I'm going to cover some additional aspects that supplements very well with our existing core platform that supports UberX and Uber Pool, which is for the HCV product that we're building. Give me a show of hands. How many of you are engineers so that I know how detailed I can get into? Okay, great, cool, thanks. So as Eoin has mentioned, the overall matching team has evolved from when I started 4 years ago, 10 lines of code doing haversine distance-based dispatch to a huge multiple services SOA architecture that talks to each other to solve this complicated matching problem instead of request greedy for all the product that Uber supports, including UberX, Pool, Eats, and now HCV. So today I'm going to talk about mainly 3 things in specific that are not what we built originally for UberX and Uber Pool. Specifically, we're going to cover dynamic versus fixed routes, the fleet movement, as well as the route management. First of all, let's talk about dynamic versus fixed routes. There's a personal story that I would like to share. A lot of people ask us, why don't we just build, because it's a Uber bus system, why don't we just build a fixed route bus system? So I grew up in China in the 80s. Back then, it's one of the largest cities in Beijing. It's the capital. We have a handful of buses roaming around the city, covering the majority of the metropolitan areas. I'm really close to my grandparents. I visit them almost every week. Unfortunately, even though it's only 5 kilometers away from each other, there's no direct bus that takes us directly to my grandma's place. I have 2 options back then. One is take a taxi. Obviously, the car will be right in front of my house and then take me directly to my grandma's house, but I couldn't afford it because I was a 5-year-old. So instead, the other option that I have is to walk 10 minutes from an apartment building to this bus stop and then take another bus for another 20 minutes, depending on how long I wait for the bus. The bus will drop me off about 10 minutes away from where my grandma lives, and then I'll walk the last 10 minutes to my grandma's house to see her. Not ideal. The alternative is also, there's actually a third option, which is I can take a bus to some other locations, transfer to another bus in order to get there to minimize my walking distance. So this basically summarizes the problem we're trying to fix with dynamic routes. So here's the first world problem that we use if we were to launch Uber bus in San Francisco. The green dots over there is one of the common area called Mission Bay. It's where the greatest Golden State Warriors is going to be moving into. And here's the pre-selected routes that we defined from Caltrain station, where most of the SF commuters are going to get off the Caltrain and then spanning across the entire city to go to their work. And we chose Caltrain, Stripe, which is a company, Zynga, Costco, and then back to 1455, which is the Uber headquarters. So for fixed routes, imagine a rider wants to, instead of going to Zynga, he wants to go to, there's one coffee shop over there. I think it's called Sightless Coffee. Unfortunately, you can't really take this Uber bus if we had this Uber bus route. The reason being it's a fixed route. The bus driver can only drive on the route. There's no deviations from the route. What would happen if we change the route on demand by telling the drivers, depending on the demand pattern in the car? So let's say in the backend system, we constantly look at all the demands and then realize that there's no rider who are actually trying to go to Zynga and Costco, but instead there are employees from Airbnb who wants to stop by Airbnb before dropping off the rest of the riders at 1455 Market Street. We can actually make that happen. From an implementation perspective, the difference is initially it's a chain of nodes, and then the out degree of every single node is limited to 1. But in this DAG dependency acyclic graph approach, we are actually increasing the number of out degrees from 1 to many, depending on how many dynamic routes we want to enable for a particular bus route. In this case, if someone wants to go to Airbnb, after we drop off people at Stripe, we can just tell the driver, send a notification, and update the navigation within the driver app and say, take a detour to Airbnb first, stop by that coffee shop as well, before heading back to 1455 Uber. Everybody with me? Cool. So with the dynamic versus fixed route, we also ran into the issue of how we actually want to manage all these routes. We have many, many routes that we have to take care of, both existing routes and also routes that are new that hasn't been covered by existing routes. So here's a map of Egypt, Cairo. That's the first city we launched UberBus to. The reason why we have this graph here is we want to show you how we actually generate the routes for the buses. So every single line here represents an existing Uber trip. So intuitively, the darker the line, the more trip has been completed on that particular route. So what we can see here is there are three pockets. There are three pockets of routes that are very, very dark. If we don't look at any additional data, we are most likely going to launch a bunch of bus routes within these three pockets. You might ask, what happens to those really light lines in between these three pockets? So initially we thought those are just outlier of the data. We should really just filter out this data. But in fact, through user research, we find out that those are normal commuters accidentally requesting Uber trips because it's so expensive in Cairo. They couldn't afford it on a daily basis. So occasionally they will take a Uber trip, drawing a very light line in between these three pockets. And through user research, we actually understand that there are more of those trips than trips that's actually happening within these three dense areas. In fact, the three dense areas represents business trips. So the main one in the center with the star in the middle, those are the area, business trips happening between Giza, which is one of the main cities, to Cairo downtown. So a lot of people are living in Giza and then travel to Cairo downtown just for business trips. That's how they can afford to take the Uber trips over there. So to summarize what I was just saying, we are basically generating routes by feeding into data from both existing Uber trips as well as user feedback into our route generation engine. And the route generation engine is going to eventually yield the routes. But we don't really just stop there. Of course, we trust our algorithms to generate the routes and we tell the rider where to walk to. But this is not ideal because we actually need people on the ground to tell us whether it makes sense or not. Here's another personal story. Before we launched the Uber bus product in Cairo, Egypt, we all flew in there. And using our algorithm, we figure out one bus stop that's at an intersection on the map. We can't really tell because Google Maps can't really tell the difference. When we actually show up in the city, checking out every single bus stop, this particular bus stop happens to be getting stuck in between two right turns. There's an immediate right turn and there's a right turn with a slightly larger angle. Obviously, we don't want rider to walk across the street where buses are turning at the immediate right turn. So that bus stop from the algorithm doesn't really make sense because Google Maps doesn't have that data. So what happens is we enable our local operations to actually walk to every single bus stop that we decided, and then can manually using human intervention to override the bus stops that we generated. So we do this for all the bus stops on the existing route and also the new routes that we're trying to generate. And then on top of that, local operations can also decide whether we want to add the bus stop on the existing route or creating new routes. So here, after we generated all these routes, another problem it's not really a problem, it's actually a good problem to have, is Uber has historically been built on top of Hexagons, which is the smallest geospatial unit that we have. The reason why we use Hexagons is for engineers in this room or people with math background, the center of the hexagon have equal distance to all the vertices within the hexagon. This has make our pricing work and dispatch work so much easier. But with Uber bus product, the dynamic routes and all the bus stops, not only do we need to change the state machine, we also need to expand the concept of geospatial, hexagons being the smallest geospatial unit to incorporate routes, which expand across different hexagons and cluster of hexagons. So far I've talked about dynamic route versus fixed route and the route management piece. Now we need to think about the problem of how to actually map the supplies or the buses to each individual routes. The goal we're trying to achieve is, on the one hand, we want to improve supply utilization, meaning that we want to put more people in the bus. On the other hand, we want to make our walking make sense for people, minimize the walkings for individual riders. The problem we're trying to solve, I summarize two problems here. One is, you can look at the lower half of the graph here. We call them bus bunching. Miraj talked about an example through user research, which is sometimes the bus will arrive with a 25 minutes interval, but most of the time is 5 minutes. But in this case, if you happen to fall into that P90 scenario or even P99, you will hate the bus because you have to wait, especially in Seattle when it rains really bad, wait for 25 minutes outdoor with the prior knowledge that normally it's okay. You're basically trying your luck. So what we want to do with Uber Bus is dynamically allocating the bus on the particular route. We can actually tell the driver at a bus stop, wait a little bit, because there's a previous driver that's only 5 minutes away from you. We do not want the bus to get clustered together so that one bus takes the majority of the riders and the other one is pretty much free. So the second problem we want to solve happens on different routes. So let's say a bus already finished the current route. we have many choices that we can take. One is we can tell the bus to go heading back to the original stop, or we can tell the bus to move to a different route where it's undersupplied. Undersupply means there's not that many buses already on the route. So in this case, if we already have many, many buses on Route B, it makes more sense for us to send our buses after completing the current route, dropping off all the riders on the route, to a different route to sort of balance the ETAs for riders on Route A so that riders could benefit. Well, with that, I'm going to hand it back to Eoin to talk about the future work of Uber Bus.
Thanks, Danny. So something we're super excited about is expanding the ways that people can use Uber to travel around cities. So Uber Bus is another example of this. And we're hoping to use this to expand access to Uber to a whole new cohort of riders of this. But piecing all the work we've done together in Uber Bus with the work we've done on Uber Pool and Express Pool, something we're incredibly excited about is heading towards Uber as a platform. Our CEO, Dara, has talked multiple times about the platformization of transport and what Uber can do. And we're really excited about the future of stitching these modes of transit together, adding in bikes, scooters, pool, express pool, high capacity vehicles, transit information in cities like Denver.